Okay, so the tank's originally half full of 2% solution, and the outflow rate's only 4 gallons per minute. What are we going to do with that? Well, it should be clear. Remember, you got your general equation is dq dt equals C1 R1 minus Q over V times R2. Very simple equation, not something you want to memorize, something you just want to understand, although if you also memorize it, it's okay, as long as you understand it. As long as you can see exactly what everything means, so that if you don't have the equation in front of you, or if you forget it, you can figure it out again, okay? It's all common sense, but not trivial common sense, obviously. Okay, so we've got this equation, but now V depends on T. Okay, it changes since R1's not equal to R2. So my question is, everything else is the same. You still have Q over V, it's just that V isn't just a symbol, it's a function. Okay? But R1 and R2, just as they were, so C1, just you got this entertaining anomaly here, okay? And that's certainly a situation that's not uncommon. Okay, so, you got muddy water flowing into South Holston, okay? And it's coming in fast, and you're trying to control flooding, so you're not releasing water as fast as it's coming in. They don't have instantaneous mixing. Okay? Although if it's a long-term thing, an instant might be a month. Not likely with weather patterns, but you can still model it, okay? So, what is your function V of T?
50 plus T, right?
What?
It's half full tank, right? So
50?
It's 50 gallons plus, plus 5T minus 4T.
Yep.
So just 50
Exactly.
plus T.
Yeah. You're gaining 5 gallons a minute, you're losing 4, you're gaining 1. So I actually change the conditions a little bit so we have something besides a 1. Okay? So V of T is 50 gallons, which is what you start with. Plus 2 gallons per minute times T, where T is implicitly now in minutes. Otherwise, this wouldn't be compatible with this. If you multiply gallons per minute by hours, you're not going to get gallons. Okay? So now, what's your equation? So equation becomes and I'm writing the units, but we'll suppress the units in a minute when we double check them. Okay? But 5 gallons per minute minus Q over this, right? So dq dt equals 0.5 minus q over 50 plus 2t times 3. Okay. Now this equation is no longer separable. You're not going to be able to rearrange things so that you can split, so you have a product here of a Q part and a T part. They're mixed. Okay? So, how do we solve this? The equation is no longer linear. Okay. Actually, okay, you treated it it's linear Q. So you got Q prime plus this equals this. How do you solve this? This is a form Q prime plus P of TQ equals G of T. Of course, G of T is just a constant. Okay? How do you solve that?
P of T.
Yeah. Which is, that's your integrating factor. Well, integral of this is just another natural log. So it's e to a natural log, and e to a natural log of something is just that something because e and the natural log are inverse functions, right? Okay? So, I'm probably going to assign you to finish that. Okay? It's not hard. Okay, well, that's one twist that you can throw into this. Another twist is that you don't have a constant inflow rate. Okay? So let's just say the inflow is exponentially decreasing. So let's worry about that a little. Okay?
We still. At this point, we still haven't included the 2% solution. Like, haven't.
That's an initial condition.
Yeah.
You solve the equation, and then you use that
Okay.
to,
All right.
you're going to get an integrating factor, essentially. You're going to get one unknown parameter, and you've got to then fit your solution to fit, fit that parameter
Yeah.
so that Q of 0 is 2, same as before. So that's not going to be different, but
Okay.
your function's going to be different.
Yeah.
Okay? Well, let's look at Okay, R1, your inflow rate is this. Okay? That's a exponential function with a half-life of about around 70 minutes. Okay? Now in 70 minutes, yeah, this thing wouldn't be full if you start half full. Okay? Not with the decrease. It'd be pretty close. It'd be pretty close to getting full. And of course, you have to calculate that too. But then, just to make it really a little more complicated and something I'm not sure we have the means to solve. Okay, if you just have this, well, that's just going to affect the non-homogeneous part of your equation, right? Okay? Then, you integrate your inflow rate with respect to time to find out how much has flowed in up to time t. That's something should be pretty intuitive, but you should also be able to do the rigorous calculus to prove it. But that's what it is. Okay? And I use tau instead of t as a dummy variable because t is the limit on the integral. We don't want to have the same variable here as we do here, so we just pick some other symbol to integrate with, okay? So replace t by that symbol and it works. Okay, well, that's an easy integral, right? So there's no problem with that. And then, then you have dq dt equals suppressing units, and I should have put 0.01 per second per minute times t, okay? To be completely rigorous with the units, sometimes you need to do that. Right now we'll suppress it, okay? So you get 5e to the negative 0.01 t. And it would be actually, because of the 10% solution, it's 0.5 gallons per minute times this decreasing exponential. Okay? So dq dt equals this minus, and it's going to be 0.3q because we're leaving the inflow rate the same. We're going to have a 0.3 on that. No, it's 3. Never mind. I should have written this a little further over. A little careless. Over. Well, I'm just going to say v of t, and you've got, of course, to replace v of t with this, right? There's your equation. Oh yeah, and v of t is this plus the 20 gallons you started with, right? So, your V of t is just still much like it was over there, you just have an exponential function, right? An exponential function in the denominator. That gets a little trickier, but you still integrate it. Okay? So, that becomes q prime plus 3q over 20 minus 3t. Actually, it might be a little trickier to integrate because you got the t in there. Plus whatever your antiderivative is here, and it's pretty straightforward what the antiderivative is going to be. Your 5 is going to come out of here, and you're going to get, you're going to let u equal this. So du equals 0.01 d tau. So d tau is 100 times u. Okay? So it's going to be 500 That's not going to be right. I'm just going to put that down there. Doing that in my head, I need to write it out. I should be able to do that easily. Not exactly sleep deprived, it wasn't a great night, I'm not going to try it. Okay. And then this is going to be 0.5 e to the negative 0.01 t. So whatever you get when you integrate this, if you can integrate it, which I suspect you can, okay? It's just going to be an antiderivative of that. It's going to be something times e to the negative 0.01 t, right? So you're going to have a power function and an exponential in a denominator. It's just an exponential, you could deal with it. Power function. I think you're not going to be able to get that, and now you're going to have to go to numerical methods. Okay? I can't off the top of my head think of a method that would solve this equation. You got to integrate this thing in the denominator to get an integrating factor, and you can't integrate it. Okay? So as I say, it's real easy to come up with a situation where you can't do it. Okay? Now, if you had a tank here, and you're letting gravity feed this into your tank down here with the outflow. So this is the same tank as before. Then R1 would be a quadratic function. Now if R1's a quadratic function, then your volume down here is going to be a quadratic function, right? Just 20 plus whatever this quadratic function is, and this is still constant. Of course, this could be feeding out by gravity, okay? Which would mean this would be quadratic, but your volume would still be quadratic. It'd just be one quadratic minus another, okay? So let's just think, if V of t is quadratic, is that a problem? Well, you can do partial fractions and integrate a quadratic, okay? That's a standard method. That's why I said review partial fractions, because quadratics come up a lot, and sometimes they're in the denominator, and you got to integrate them, okay? So that would be no impediment as long as this thing is nicely behaved, but this is also quadratic, okay? So chances are you'd be able to solve the problem. That give you kind of an idea of what you're up against with mixture problems. The idea is simple enough. Of course, then later in the course, hopefully, I don't know that it's in the syllabus, because it's in the VCS course description because we dumbed the course down. But you do, and we dumbed it down with the approval of this Virginia Tech and other schools. Okay, so we don't care. Just as long as I've had a differential equations course, we're happy. And yeah, depending what kind of engineer you want to be, if you're good enough to be the kind of engineer that really needs it, then you'll be able to figure it out when you see it. And you get it in a more advanced engineering math course. But if you have a network of tanks, with tanks pumping back and forth among one another, then you have a system of differential equations. And they're fun. I love them. But it seems like I probably won't get to spend much time on it.
Would you use that in the case of hydraulics?
Well, in
Flowing into a hydraulic
hydraulics,
cylinder.
everything is confined.
Yeah.
So it's pressure that's being enforced. It's,
Yeah.
yeah, so, no, but when you're designing a hydraulic system, and I'm doing this off the top of my head, I've not dealt with hydraulic systems, you do have issues with viscosity and pressure loss as you pump from one chamber to another. And you have to deal with those things in some way, at least approximately, so you're sure you're over-designing the system. And have a pretty good idea about what factor you're over-designing it, okay? There's still things that you just can't get a handle on. You can only approximate. So that's just my, off the top of my head, response to a good question. And I'm sure there are things I didn't think about in the instant I spent on it, okay? But that's my first instinct. And you got compressibility, any fluid's compressible. That's usually not an issue, but if you get into really high pressures, it can be an issue. Okay? It depends what your hydraulic fluid is, but they're close to incompressible. Almost any situation I can think of, you're not gonna.
Yeah, we test anywhere from like 3 to 5,000 psi.
Yeah, that's nothing.
Yeah.
Take the pressure at the bottom of the deepest part of the ocean.
Yeah.
You get a little bit of compression, okay? That's way over thousands of psi.
Yeah.
That's in the tens of billions. Well, let's see, what is it? 10,000 meters depth, okay? Then you'd have for every meter of depth, you get 10,000 pascals. So you got 100 million pascals, okay? Which is 1,000 atmospheres. Seems it ought to be more than that. Which would be 14,000 psi, okay? So it wasn't in the millions. If I did that calculation correctly, that's pretty simple. But again, I'm not 100% right now. So don't quote that, and don't be designing your next hydraulic system based on my somewhat unreliable response, okay?
Yeah.
It's a good question. Okay, so anyhow, this, sometimes you can do it and sometimes you got to approximate it. Okay? Now you've got your textbook. I'm going to assign problems from various parts of Chapter 2 that I think you should be well prepared to do. I might give you a couple out of Chapter 4 too, since you've already got the technique down. Just straightforward problems just to show you that, yeah, you learned something in the last couple of weeks. And then we'll get more methodical about how we go through things. Chapter 3 is a bunch of tricks for solving various types of differential equations. Chapter 4 is higher order equations, well, second order equations, okay, which you already know a lot about. Okay? Good.